all of our trig graphs, and we've talked about this already, have real-world applications whenever we have a situation with a recurring pattern. So I'm going to give you an example of a situation with that's really easy to visualize. And then I'm hoping that you can take this example and then apply it to other things that are recurring. Okay, so this is an example of a Ferris wheel, just because it's easy to imagine. You got a Ferris wheel, we've all been on them, or watched them anyways, go round and round. So Carolee gets on a Ferris wheel at the bottom at time t equals 0. Ferris wheel has a radius of 13 meters. Its center is 15 meters off the ground, and it's a really fast Ferris wheel. It takes 32 seconds to complete one rotation. Okay, so let's just draw a little picture of what we're talking about here. So we got a word problem. Let's try and draw a picture. So here's a Ferris wheel. I'm going to give it a base. Here's the ground. Okay, so it tells us that this Ferris wheel has a radius of 13 meters. So from the center to the edge, 13 meters. And it tells me that the center of it, so I'm just going to measure height right here. This center of this wheel is 15 meters off the ground. How far is the bottom of the wheel off the ground?
2.
Okay. And how'd you get that? Well, you just subtracted 13. And why isn't the wheel on the ground? Well, because if it was right on the ground, then we'd cut Carolee's legs off when it came around to the bottom. Okay, so we put the Ferris wheel up a bit. Okay, tell me what the maximum height is, because Carolee's scared of heights. How high is she going to go up up in the air? Okay, we all agreed? She goes up to 28 meters? Okay, so that's pretty high, isn't it? What's that? Okay, we've got a picture physically. Now let's put time into there. So if she's getting on at the bottom, and I'm going to just mark time here in 0, then I'm going to ask you for a couple of different times. What is the at what time is she 2 meters off the ground? 0. I'll give you that answer. How long will it take for her to make one complete rotation? 32 seconds. How long until she is 28 meters off the ground, right up there at the very top? 16 seconds. How long until she's 15 meters off the ground? How'd you get that? It's a quarter of the period, isn't it? And then actually that happens twice, doesn't it? Because she goes up to the max, she's real scared, and then she starts coming back down. So what time does she reach this again? Okay, so you took the period 32 seconds, and you divided it into 4. It's from the bottom to the center to the top to the center to the bottom. Okay. All right, so there's our picture, and what are we asking us to do? Sketch a graph of the wheel's motion, and we got to put in 5 points. Okay, so right here, I need to graph Carolee's height. And we're going to graph this in meters. Of course, a graph means nothing without a scale. So we're graphing her height in meters. And we're going to graph time in seconds. So label both of these with your units. Okay, so one complete rotation then. I'm going to start here with time is 0. And 1, 2, 3, 4, 5, 6, 7, 8 seconds. 9, 10, 11, 12, 13, 14, 15, 16 seconds. 17, 18, 19, 20, 21, 22, 23, 24 seconds. Okay, all the way to 32 seconds. Okay, so there's my scale along the x-axis. Along the y-axis, I need to go from, I'm going to go from 0 to 28. And do I have room for that? I don't. So I'm going to have to go every 2 meters. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, up to 30. All right, then let me look at both of these at once. And I'm going to do a sketch, and it says I need to get 5 points accurate. 4 points accurate. Where do we start? We start when time is 0 and her height is 2. When time is 8 seconds, her height is 15. So at 8 seconds, her height is 2, 4, 6, 8, 10, 12, 14, 15. When time is 16 seconds, her height is 28. And back to time is 24 seconds, her height is back to 15. And then at 32 seconds, she's back to being 2 meters off the ground. Hopefully there's a platform to get her down. Okay, so what's her height as a function of time? Well, her height starts here at 0, and it goes up to 8, and up to a max of 16, and then comes down to back to, sorry, I said 8 and I meant to say 15, and then all the way back to the bottom at 2. Okay, so there's a sketch of her height as a function of time. How would you describe that function? Looks like an upside down coast curve. Okay, so we're going, let me just give you a vocab word. Sinusoidal means it repeats. It's not something wrong with your sinuses. It means that the pattern keeps on repeating like a sine function. And we talked about this when we graphed sine and we graphed cos. Sine function, cos function, they're really the same wave with a phase shift. So you get to choose how you want to model this. Do you want to call this a sine or do you want to call this a cos? It just depends on what's the easiest for you. Okay, and your graphing calculator. Okay, so if we're going to graph this as a sine, if we're going to write an equation, and in fact I want you to get practice on doing both, then we need to graph either y equals a, amplitude, sine, or we could use cos, square brackets b, x minus c, plus d. Okay, how are we going to know the amplitude? So part B, finding an equation that models this situation. We need to know what's the amplitude. Well, it's the absolute value of the max minus the min divided by 2. So tell me the amplitude. Is everybody getting that? Okay, then your displacement is like your average value for this function. It's your max plus your min divided by 2. What's your displacement? In fact, you can see it on there. Where's the centered around? 15. Okay. So given that, we can write a function for height at any time t. H at t, so here's our function, height at any time t is going to equal our amplitude, 13. And then if I model this, I'm going to actually model this as a cos curve. I need to know the b value, I need to know the t and the phase shift, and then add the amplitude. Okay, how am I going to find the b value? Well, remember that in order to find b, it's 2 pi divided by the period of the function. What's the period of this function? How long until we've completed a cycle? From the bottom to the center, to the top, to the center, back to the bottom. 32 seconds. So B is 2 pi divided by 32. Reduce your fraction if you like. Pi by 16 is your B value. Okay, you guys just finished a graphing quiz where you had a lot of trouble setting up your x-axis. The scale was hard to work with. Do you notice what our scale is? It's just seconds. It's not pi by 12 seconds or pi by 360 seconds, which would be really, really hard to work with. It's actually 1 second, 2 seconds, 3 seconds, all the way to 32 seconds. So how do we get a scale that's so simple like this and not pi's in it? It's because the B value has the pi in it. Okay, so my B value, this is saying I've got a horizontal compression of pi by 16. Sorry, I don't. I have a horizontal expansion of 16 over pi. And that dividing by pi has taken the pi out of your scale. Okay? So from here we've got our B value. Now we're going to look at our graph and find the phase shift. If it's a cos graph, then it should look like this. What does cos look like? It starts at the top. And this is not starting at its max. How far do I have to shift my cos graph to get it to start? I have to shift it 16 seconds. Could you please, since I've done most of the work for you, tell me what your sine graph would be? I'll get you started. Same amplitude, same B value, same displacement. What's the phase shift if it's a sine graph?
8.
And which way? Minus, because you want to go right. We all good with that? Okay, next we're going to put this into our graphing calculators. Okay, so take your graphing calculator, and I want you to pay close attention to this because it's probably one of the big places people get stuck, is how do you enter this equation? And funny enough, I find that the mistake people make is they use too many brackets. So we want 13 cos, and notice it's already open up for us. Put your B value in. It is pi by 16. I do need brackets on my phase shift. Bracket T minus 16, close both brackets before add the displacement. Okay, so one more time, you're basically doing it exactly like you see it. 13 cos, the bracket's open, and you put in your B value, pi by 16. Yep. Sure. And then once you've got your B value in, you need to open brackets for this and put in your x minus 16, and then both of them close before you add your displacement. If you are in radians mode already, good. If not, switch. And then unless you change this window to something that makes sense, you're not going to see anything. Because if I just did a zoom 6, a standard window, I'm really not seeing Carolee go around a Ferris wheel. It looks kind of like a parabola, actually. It's not, but it kind of looks like it. So think about what we're graphing. We're graphing her height as a function of time. So the x values are measuring time. Where should I start time? 0. And if I want to see one complete rotation, where should I end the time? One complete rotation, 32. Okay, then if the y values are measuring the height, what's the minimum height we want to look at? Or I'm going to look at 0, not too far off. And the maximum height? 28, or I'm going to look a little bit above to 30. Okay, there's a complete rotation.